Deep learning is a subfield of artificial intelligence, AI, that is inspired by the structure and function of the human brain, specifically the neural networks that make up the brain. It involves training artificial neural networks on a large data set, allowing the network to learn and make intelligent decisions on its own. Deep learning has revolutionized many fields, including computer vision, natural language processing, and speech recognition. It has also been used to create self-driving cars, improve healthcare, and more. The basic building block of a neural network is the neuron, which is a simple mathematical function that takes an input, processes it, and produces an output. These neurons are organized into layers, with the input layer receiving the raw data and the output layer producing the final result. In between these two layers are one or more hidden layers, which process the data and pass it along to the output layer. The process of training a neural network involves feeding it a large dataset and adjusting the weights and biases of the connections between the neurons. That is done using an algorithm called backpropagation, which compares the predicted output of the network to the true output and adjusts the weights and biases accordingly. One of the key advantages of deep learning is that it can automatically learn features from raw data, without the need to manually feature engineering. This allows it to handle very complex tasks such as image and speech recognition that would be difficult or impossible for a traditional machine learning algorithm to perform. There are several types of generative models that can be used to generate images. Generative models are a type of deep learning model that can generate new data that is similar to a training set. One application of generative models is the generation of images. Generative adversarial networks, GANs, consist of two neural networks, a generator and a discriminator. The generator generates new images while the discriminator tries to distinguish between real and generated images. The two networks are trained together, with the generator trying to produce images that are realistic enough to fool the discriminator, and the discriminator trying to accurately distinguish between real and generated images. Variational autoencoders, VAEs are a type of generative model that uses an encode-decoder architecture. The encoder maps an input image to a latent representation, and the decoder maps the latent representation back to an image. VAEs can be trained to generate images by sampling from the latent space and feeding the samples through the decoder. Autoregressive models, regressive models such as Pixel CNN and WaveNet generate images one pixel or sample at a time, using the previously generated pixels or samples as context. Deep learning involves training artificial neural networks, which are composed of layers of interconnected neurons that process and transmit information. A neural network takes in input data and applies a series of transformations to the data, passing it through multiple layers of neurons before producing an output. The output can be a prediction, classification, or some other type of computed result. The process of training a neural network involves adjusting the weights and biases of the connections between the neurons so that the network can accurately map input data to output data. This is done using an algorithm called backpropagation, which compares the predicted output of the network to the true output and adjusts the weights and biases accordingly. One of the key advantages of learning deep learning is its ability to automatically learn features from raw data, without the need for manual feature engineering. This allows it to handle very complex tasks such as image and speech recognition that would be difficult or impossible for a traditional machine learning algorithm to perform. Deep learning models can be trained using various types of data, including structured data such as tables of data and unstructured data such as images and text. They can be used for a wide range of applications, including image and speech recognition, natural language processing, and even playing games. One of the main challenges in deep learning is the need for large amounts of labeled training data. Neural networks require a significant amount of data to learn and make accurate predictions, and the quality of the data can have a big impact on the performance of the model. Another challenge is the computational requirements of deep learning. Training deep learning models can be resource intensive, requiring powerful hardware and lots of time. However, advances in hardware and software have made it increasingly feasible to train large deep learning models. I hope this gives you a thorough understanding of the basics of deep learning and how it functions. There are several techniques that can be used to improve the performance of deep learning models, including data processing. Pre-processing the data before training the model can help improve performance. This can include techniques such as normalization, standardization, and augmentation. Model architectures. Different model architectures can be more or less effective for different types of tasks. Some common architectures include convolutional neural networks, CNNs, for image tasks, recurrent neural networks, RNNs, for sequential data tasks, and transformers for natural language processing tasks. Hyperparameter optimization. Deep learning models have a number of hyperparameters that control their behavior, such as learning rate and the number of layers. Choosing appropriate values for the hyperparameters can significantly impact the model's performance. Regularization. Regularization techniques such as dropout and weight decay can help prevent overfitting and improve the generalization of the model. Ensemble methods. Combining the predictions of multiple models can often improve performance, especially if the models are diverse and make different types of errors. Transfer learning. Pre-trained models that have been trained on large data sets can be used as a starting point for training on a new task, often allowing for faster training and improved performance. In addition to the techniques mentioned above, there are a few other considerations to keep in mind when working with deep learning. Hardware. As mentioned earlier, deep learning can be resource intensive, and having access to powerful hardware can make a significant difference in training time and model performance. Options include using a local machine with a high-end GPU, using a cloud service with GPUs, or using a distributed system with multiple GPUs. Software. There are many deep learning libraries and frameworks available, including TensorFlow, PyTorch, and Keras. Choosing the right library or framework for your needs can make it easier to build and train deep learning models. Data labeling for supervised learning tasks. The quality of the labeled training data can have a big impact on the performance of the model. Ensuring that the data is accurate and representative of the real-world task is important. Explaining model decisions. Deep learning models can be difficult to interpret as they are typically black boxes that make decisions based on complex interactions between the input data and the model's internal parameters. Techniques such as feature visualization attribution methods can help provide some insight into how the model is making decisions. Some other things to consider when working with deep learning include validation and testing. It is important to evaluate the performance of a deep learning model on a separate data set, known as the validation set, in order to ensure that it is generalizing well to new data. The model should also be tested on a holdout dataset, known as the test set, to get a final estimate of its performance. Overfitting and underfitting. Overfitting occurs when a model is too complex and has learned patterns in the training data that do not generalize to new data. This can lead to poor performance on the validation and test sets. Underfitting, on the other hand, occurs when the model is not complex enough to capture the underlying patterns in the data, resulting in poor performance on the training set. Bias and variance. Bias is the error produced by oversimplifying the model, while variance is the error introduced by making the model too complex. Finding the right balance between bias and variance is important for good model performance. Data imbalance. If the training data is imbalanced with some classes having much more data than others, this can impact the model's ability to learn, and generalized techniques such as oversampling and undersampling can be used to address this issue. Even more things to consider when working with deep learning include feature engineering. Depending on the type of data and the task at hand, it may be necessary to extract relevant features from the raw data in order to feed them into a deep learning model. This process, known as feature engineering, can be time-consuming and requires domain expertise, but can significantly impact the performance of the model. Model interpretability. As mentioned earlier, deep learning models can be difficult to interpret, which can make it hard to understand why the model is making certain decisions. This can be especially important in fields such as healthcare and finance, where the consequences of incorrect decisions can be significant. Ethical considerations. Deep learning models can be biased if the training data contains biased or stereotypical information. This can lead to unfair or discriminatory decisions, and it is important to consider the potential impacts of a model on different groups of people. Data privacy. Deep learning models often require access to large amounts of sensitive personal data, which raises concerns about data privacy. Ensuring that data is protected and that appropriate safeguards are in place is important.